So now we're going to cover 4.5. And this is the last section before the exam. It'll probably not be, it won't be next week. We'll do it the following week, and I'll have more details on that a little later in this week or early next week probably. Give you plenty of time for questions and stuff. All right, so this is 4.5. This is on exponential and logarithmic equations and applications. So exponential and logarithmic equations and applications. Not sure how far I will get in this video. We'll certainly do the equations part. We may do another one for applications. So we'll see how this goes. All right, so first, if you have an exponential equation, so and I'm going to let capital X and capital Y be real numbers. Or they can be basically like an algebraic expression, but they're real. We have b greater than 0 and b not equal to 1. So same hypothesis basically as the base of an exponential and log. So if you have similar bases, you have b to the x equal to b to the y, then that is equivalent to x equals y. So if you have the same bases, then right here and here, if they're exactly the same, then you set the exponents equal. So that's the concept. All right, so this is what we would refer to as similar bases. All right, so for similar bases, we have, let's just check out some examples. All right, so first example, you're asked to solve something like 4 raised to the 2x minus 3 equal to 64. So you can see right there that 4 and 64 are not the same base, but what can we do to convert 64 to the same base? So we want to, what I'll say, get the same base. So to get the same base, we want to say what 4 to what power, because we want to use 4, right? So 4 to what power is 64? So you'd mess around a bit and you'd say 4 cubed is 64. Right? So we're going to use that in its place. So that's equivalent to 4 raised to the 2x minus 3 equal to 4 to the third. So now that these bases are the same, we can set the exponents equal. So what we do is we want to set the exponents equal. So that's equivalent then to 2x minus 3 equal to 3. And then you solve. Okay, and then you solve that equation. All right, so you get 2x equal to, add 3 on both sides, and you get 6, and then divide by 2, and x is equal to 3. All right, so we get x equal to 3. So with exponentials, since the domain is all reals, whatever you get, that's it. That's the solution. So we can use the solution set and say that that's the solution 3. All right, let's do another one for similar bases. Okay, so next example, solve 27 raised to the 2w plus 5 equal to 1/3 raised to the 2 minus 5w. So again, we have or want to get 27 and 1/3 to be similar. So we got to realize that 3 is going to be in common of some sort. So we know that 3 cubed is 27, and we can write 1/3 as 3 to the negative 1. So then, in that case, the base will be the same. So once you get the base the same, then you can set the exponents equal. So you got to replace that directly with 27 and 1/3. So it'll look like this. So 27 is 3 to the third, and then that is raised to the 2w plus 5. And then 1/3 is 3 to the negative 1, which is raised to the 2 minus 5w. So from there, you would use the power to a power property. So if you have basically x to the n raised to the m, then we say that's x to the n times m. So you do that product. So it's 3 raised to the 3 2w plus 5 is equal to 3 raised to the negative 1 times 2 minus 5w. And then we distribute the 3, and you can set them equal right now. I mean, this is fine. Right now you have this and this, and you can set them equal at any point. That's probably the best thing to do at this point, is go and set those equal. So you get 3 times 2w plus 5 equal to negative 1 times 2 minus 5w. And then solve that. All right, so maybe at this point, go ahead and try that, and solve that. Maybe pause the video and solve that. Okay, so then we get 6w plus 15 equal to negative 2 plus 5w. Isolate w on both sides, so w is equal to subtract 5 on both sides, subtract 15, and you get negative 17. So that's the solution, is negative 17. Okay, so that's one of our techniques, is similar bases. The next technique is going to be unlike bases. So that's the other type. The next is, let me get rid of that. So we just call these unlike bases. So for unlike bases, then you have to use a completely different technique. Well, not completely, but it'll look like this. All right, so our example, solve. You'll see what I mean when we mean unlike. There's no way to get them to be the same. So suppose you have 5x equal to 83. So there's no way to get, for 5 to be a power of 83, 5 to be a power, you're going to have a 0 or 5 in it. So there's no way it's going to be 83. So these are completely different. So the first way to do this concept is use the the definition. Okay, so put it over here. Use the definition. So what I mean is, if you have z equal to log base b, actually I think I did it like this. I used w, didn't I? So w is equal to log base b of z. That's equivalent to b to the w equal to z. So the base, no, that's not right. Try that again. That's, I'm sorry, I had that right. Sorry, b, so it's the power. Log is the power, so b to the w is equal to z. So that's the definition of the correspondence between a log and an exponential. So we can write that directly as I always start with the base because it's kind of easy to see. So if you would say log base, and then you say 5 because that's where it is, right? So you see base here, of of what it equals is the exponent. So you say log base 5 of 83 is equal to the exponent. And then we can simplify that and get an approximation. So we can say x is equal to log base 5 of 83, and we can write that in exponential form. So, convert it to different base. So you can say I'd use ln, so ln 83 over ln 5. So that is equal to, and then you can convert that, or you can use log 83 over log 5. Okay, so in any case, use your calculator to get an approximation. It is 2.74558. Okay, so that's we're going to use that technique, but there's another technique we're going to use primarily. I think it's kind of the better way of doing it. So this is case 1. This would be case 2. So case 2, what we do is we take the log on both sides. So you can think of it as applying the same thing on both sides to solve it. So you have 5 to the x equal to 83. And so now usually you can take, when I say log, you can take the natural log or the common log. I usually do, like I mentioned earlier, taking the natural log because there's just 2 letters instead of 3. Like, why would you do more work and write another letter? So it kind of simplifies it to me. So if you do that, you have ln 5 to the x equal to ln 83. And then you use properties of logarithms. So we want to apply now the power property. So to apply the power property, we can bring the x, come back. We can bring this x out in front like that. So then you get x ln 5 equal to ln 83. And then divide both sides by ln 5, and you get ln 83 over ln 5. And then that's it. You can't simplify that any further. That's exact form. Let me clean that up a little bit. That's exact form. You can get an approximation if you want, but not needed. Usually the book may ask you, but I'm not going to ask you. I want you to have this exact form. This is what I'm looking for right here. Okay, so let's do another one, and you can try it. So let's call this an example. So next example. So try this one. So solve 7 to the x equals 4. Okay, so maybe what I'll do is I'll just say try it, and then once I write that, you just stop and go and do it. All right, so when you do that, now we're back. Take the log of both sides, ln 7 to the x, ln 4, bring down the x, divide, and you get x is ln 4 of ln 7. Again, this is exact form. That's what I really want to see. And then you can simplify it if you want. The book may have that. 0.71241 is what they got in the book. And that's the approximation. Okay. Let's see where we're at. All right, so that's 15 minutes. All right, so let's continue. See how far we can get here. So let's see, let's do another example. So this has base E in it. Okay, so next example, we have 5 times e to the 4m minus 3 minus 7 equal to 13. All right, so this one's a little different in that we don't have, or we have basically a base e in it, which makes it a little unique. So you can then raise it to ln on both sides and use the inverse properties. All right, so the first thing you want to do is isolate the exponential term. So the term with the exponential. So the first thing you want to do is take, this is the term here, the entire thing that has the exponential in it. These do not. So isolate this one, and then you're going to raise each side, or take the natural log of each side. So add 7. So it's 5e to the 4m minus 3 equal to 13 plus 7, so that'll be 20. And then looky there, when you divide by 5, you get 4. So it's e to the 4m minus 3 equal to 20 over 5, which is 4. Okay, and now is what you do next is take ln on both sides. So you do the ln on both sides, so it's ln e to the 4m minus 3 equal to ln 4. So it's 4m minus 3. That's in parentheses, don't forget that. Ln e equal to ln 4. Now, you may recall that ln e to anything, let's just put a purple dot up there. Okay, ln e to anything is equal to anything is to the purple dot. So whatever's up there, you get it back out. So you didn't have to do this step from here to here, really. You could have just said ln e to that, the 4 minus 3, is just that. Or you could think of it here as ln e, and that's really to the 1, is equal to 1. So that's just going to be just a 1 there, and just appear. So you get 4m minus 3 equal to ln 4. So now you want to solve for m. So 4m equal to ln 4 plus 3. And then just divide by 4. So m is equal to ln 4 plus 3 divided by 4. Okay, and that's it. That's your exact solution. Okay, next case. Let's do another example. Let's solve for x. All right, so suppose you have 3 raised to the 2x plus 5 equal to 2 to the x plus 3. All right, so same process applies. You want to take the log or natural log or log of both sides, right? So take ln or log on both sides. All right, so doing that will allow us to bring down that power. So this power will bring down just like before, and then we can solve it as we did. So this is about the extent of these types that I'll give you, so expect one like this. All right, so take the ln on both sides. So ln 3 raised to the 2x plus 5 equal to ln 2 raised to the x plus 3. And then you bring down the power, so you get 2x plus 5 in parentheses, ln 3 equal to x plus 3 in parentheses, ln 2. All right, so now the goal here is to isolate x. So to isolate x, what do you do first? Yes, you distribute first. You got to treat this ln 2 like a constant, like a or b or pi or something. So we got to distribute, isolate the terms with x on one side, and then divide out that constant or that coefficient. So it's 2x ln 3 plus 5 ln 3 equal to x ln 2 plus 3 ln 2. So now the terms with x in it are here and here. So those, let's go and highlight those. So those are the terms you need to isolate now. Okay, so we'll go and write a little recap here. So distribute, isolate these terms, and then you'll divide out by the coefficient. Again, do not convert your natural log into decimals. Leave it as one thing in exact form. So we have 2x ln 3 minus x ln 2 equal to 3 ln 2 minus 5 ln 2. So I subtracted x ln 2 on both sides and 5 ln 3 on both sides. That should be a 3, shouldn't it? ln 2, yeah, this should be a 3, huh? Right there. Okay, so you want to go back and forth, right, and double check your work as you go. Okay, so now you want to then factor out your x right here. Okay, so factor out x. Right, and we're almost done at this point. So you factor out your x. You have 2 ln 3 minus ln 2 equal to all of that. 3 ln 2 minus 5 ln 3. And now divide out by, you consider that being your coefficient. Now divide out by this. All right? So you get x is equal to 3 ln 2 minus 5 ln 3 all over 2 ln 3 minus ln 2. All right, so this is the form. So this last step here is divide out. And so this is your exact form. This is the form I'm looking for. This is what I want to see. Bummer, it didn't work. I'll just circle it like that. Okay, so this is exact, and that's what we want. Okay. All right, we'll go ahead and pause it.